Picture of J.J. Thomson, and he's credited with the discovery of the electron, and his model of the atom reflects that he discovered electrons. Okay, this is a picture of the apparatus that he used to discover the electron model, and basically what he did was there's an electric field here, right? So it's sort of a crossed fields thing, and without the electric field there, he used a magnetic field to make these particles go in a curved path. And then he put the electric field in there to make it go straight so that it would go like this, right? And it's just like that mass spectrometer that we talked about in the last chapter. What you can do is you can actually measure the charge to mass ratio. Okay, and the charge of an electron is, of course, the electron charge, and there it is. So long before we knew what the actual charge on an electron was, we knew the ratio of the charge to mass, right? And so these cathode rays were believed to, we knew they were negatively charged particles. They all had the same charge to mass ratio, so therefore they probably were all the same particle, right? And so Thomson came up with the plum pudding model that we like to make fun of, but you know, what the heck? He had about the size figured out, you know, that it's about 10 to the minus 10th meters, and electrons are neutral. So if atoms are neutral, right? So if electrons are negatively charged, then there must be something positively charged to add to the negative charge and make it neutrally charged, right? And so he imagined that there was sort of this positively charged material, and in that pudding of positively charged material, there were these little negative plums, right? Okay, so therefore electrons play a big role in his atom because he discovered electrons, right? So Ernest Rutherford decides to, you know, let's perturb these atoms, right? So he takes alpha particles, and an alpha particle is basically it's the nucleus of a helium atom. All helium on Earth is the result of, I believe, all of it, right? Of alpha decay. These large nuclei like thorium and uranium and stuff like that actually are unstable, and they'll eject these things called alpha particles, which are giant. I mean, there's 2 protons, 2 neutrons, right? And so these were the biggest bullets we had before there were particle accelerators. We hit stuff with alpha particles, right? Okay. And then this is a block of lead, and he's drilled a hole in that and stuck the radium in the back, and the particles that come out of that hole are all going in the same direction because anything not going in that direction hits the lead and is absorbed. Right, so these alpha particles are flying through this, right? And then this is metal foil. He was using gold because gold has giant, well, it's a big heavy atom, right? Okay, and he had a screen here. This is like zinc sulfide or something. And when alpha particles hit that screen, they glow. And he discovered that most of the particles actually hit right there. They went straight through and hit like that. Some of them were deflected to the side. And he kept moving the screen from side to side, and he was expecting really quite small angles of deflection, okay? Because all there were in there should have been just electrons, and electrons are quite small compared to alpha particles, right? But he kept moving the detector to the side, and the more he moved it to the side, the more he discovered that some are hitting there. Every now and then, they're hitting way off to the side. There's something big in the metal foil that's deflecting those electrons. Then he put the viewing screen behind it, and to his astonishment, some of them were bouncing off this thin metal foil, right? And bouncing back. And he, you know, he said it was as if I, you know, fired a gun at a sheet of paper and had the bullet ricochet backwards. Well, what is in an atom that's capable of deflecting a helium nucleus backwards? Well, of course, what he discovered was the nucleus of the atom, where, you know, most of the mass is, right? Okay, so this is a diagram from my old physics book showing an incident beam of alpha particles, amazingly, you know, parallel, right? Most of them go straight through, okay? Some of them are deflected a little bit, okay? And then, you know, every now and then one gets deflected backwards in some crazy angle like that, right? The thing to notice here, though, is the closer you get to a nucleus like this, the more you're deflected. But you have to get pretty close for that Coulombic repulsion to deflect you. Most of them are going to go through this foil, right? And this is why you use gold. Is that gold is marvelously soft, so you can make gold a few atoms thick. It's amazing. Okay. This is Rutherford's model, and this is the one, you know, everybody draws a picture of a Rutherford atom because what it really looks like is too bizarre, right? You can't draw a picture of it. This is obviously way off to scale. This thing should be 100,000 times smaller than the atom itself, right? Okay. And the idea was that the attraction between this, right, the force of attraction, would cause it to orbit. You know, the centripetal force needed to make it go around a circle would be provided by the Coulombic attraction, right? Okay. But it's got some problems, okay? The first question is, if you've got an electron and it's here 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 and it's here, isn't that like an antenna? Yeah? If you take an electron and oscillate it back and forth, shouldn't you be radiating light waves or photons or something like that, right? It should. If it's accelerating, if it's going like that, it should, right? Okay, it's going to act just like an antenna that we talked about in electromagnetic waves, right? The second thing was that when you took these atoms and really pissed them off and stuck 10,000 volts through a gas of these atoms, right? This is like a hydrogen atom. It didn't emit just sort of any color light. It emitted these like certain colors, right? Like red and green and blue and nothing in between, right? And as far as we could tell, this orbit could be anywhere. There should be like any type of energy displayed, right? So basically, there was no way to predict these spectral lines that we're going to talk about in the next thing, right? Okay, I won't bore you with that solution right now. And then finally, the last thing I'd like to leave you with is just an idea about how small atoms are. If they're 10 to the minus 10th meters, right? The smallest thing I think we can picture a meter stick, and I think we can actually look down here. There's a millimeter right there, right? I think we can see with our bare eye, our naked eye, right? A tenth of a millimeter, right? Okay. Well, a tenth of a millimeter is 10 to the minus 4th meters, right? Because a millimeter is 10 to the minus 3rd, right? So let's take that tenth of a millimeter, the smallest thing we can see. Let's blow it up to the size of a soccer field. Goal line to goal line, a soccer field is 100 meters. Okay, so that's a little bit of magnification. Are you picturing that? Now, let's take a stack of papers, ordinary copy paper, and let's stack it 100 meters high, 100 meters in the air, right? So there's all these stacks of paper, and we're going to, holy cow, right? There it is, 100 meters. We are standing at the bottom of the stack looking up, right? We've stacked paper 100 meters high. Well, I know I can count copies. 100 sheets of paper make a centimeter, right? And 100 centimeters make a meter, right? And 100 meters make a soccer field. Whoops, yeah. And now we are, down to from 10 to the 4th to 10 to the minus 10th meters. So if you took the smallest thing you could see and you stacked paper and you blew that up to 100 meters and you stacked paper 100 meters tall, every sheet of paper would be an atom. Thought I'd leave you with that thought. You can almost picture that, can't you? Oh, I tried. No, I can't.